So this time, so remember that last time I said the cutoff points for cuts. I said this last time. But the places where those subfunctions change on those piecewise distributed functions are locations of point forces, locations of point couples, and places where distributed load functions change. Okay, so now we're going to talk about internal loads with distributed loads. So let's say internal loads in the presence of distributed loads. And so here's kind of how it works. Let's say that we have a body like this, and let's say there's the distributed load. And maybe we have a force here and a force here. Okay. We're going to make a cut and look at part of this body like this. And we're going to leave out part of the body. And the piece that we're isolating has that part of the distributed load, but not this part. And it doesn't have this force. It does have this force. And then it has the internal loads produced by that fixed joint. So that's what a cut looks like when there's a distributed load. But the thing that's so notice that the height of this shape is not the height of this shape. Okay. And so what we're going to have to do is come up with a function of x that represents the height of that distributed load at a given value. So we'll always need to find the function q of x that represents the height of the distributed load for a given x. Okay, so let me show you let me show you an example of this. So let's say that we have a beam, and I'll do that triangular shape again. And let's say that the height of this distributed load is 5,000 newtons per meter. And let's say that the length of this beam is 5 meters. Okay, so what we're going to need to do is find this function q that represents that diagonal line, because that diagonal line gives the height of this distributed load at any x value. Okay, so q of x, you can see that in this case it's a line. So this is equal to mx plus b. Okay, when x is equal to 0, that's the left end. Okay, so this is x equals 0. This is x equals 5. So what's the y-intercept of this? What's the height of this distributed load at x equals 0? 0. And so in this case, this goes away. And so now q of x is equal to, that slope is just the rise over the run times x. The rise from 0 to 5 is 5,000. The run is 5 meters. So this is 1,000x. Okay. So at each cut, you'll replace the distributed load with an equipolant point force. Okay, so like once we've made this cut in this picture here with the blue part missing, once we've made that cut, we're going to replace all that black part of the distributed load with a point force. Okay, but remember that you can't make that replacement until you've made your cut, until you've chosen what piece to isolate. So I'll try to bring that out as we go, but that's sort of a key to all of this. Remember, you can't replace the distributed load with an equipolant point force until you've chosen the piece to isolate. Okay, so let's think for a second about why that is. So, because you might think for this problem, you would replace this triangular distributed load with a point force. So that point force would be acting a third of the way from the right to the left, right? And then you would do your cuts, and you do one before you got to that point force, and one after. But think about what's happening if you do a cut. So you cut this beam off before you get to that equipolant point force. The math would all think that there's no vertical force acting on that piece that you're isolating, and you can clearly see that that's not true. You know what I mean? And so what you have to do is first choose the piece to isolate. Think about how much of that distributed load is acting on the piece, and then make that replacement of that piece that's acting on it, of that distributed load that's acting on it, with a point force. Okay. That's a pretty common mistake that people make, is to make the substitution to the point force first and then do the cuts, and it's the wrong answers. Okay. So let's start with, I'm just going to start simple and move up as we go. So the first one, I'm just going to do a case where we have a beam and the only external loads acting on it, well, there's joints and then there's the weight. Okay, so let's say we have a pin over here. A roller over here. Let's say that the length is 2 meters. The mass is 30 kilograms. And we want to calculate the internal loads. Okay, so where can the subfunctions change here? Are there any places? So think of the list I gave you right at the start. Look for any places on here where there's point forces, point couples, or distributed load changes. Yep.
The mass.
So let me first draw a free body diagram of the whole thing, and then maybe that'll sort of. So the first thing is like this, okay? And that weight is evenly distributed over here, so you can just think of that as 30 kilograms divided by 2. So this is 15 kilograms per meter. And then we have a force here, I'll call that RA, and a roller force here, I'll call that RB. Okay. So are there any point forces? Well, there's one at each endpoint. But we're only interested in, so we already know that that there's going to be one subfunction that represents stuff in between those two. So those don't really change anything. Are there any other point forces in between the endpoints, or point couples, or places where the distributed load function changes? No. So that means that we're only going to have one cut here. Okay, we're going to do one cut that represents every length of this beam from just over 0 to just under 5. Okay. Before we do that, we have to calculate those external loads. So if I think of this thing, it has a length of 5, a height of 15. The centroid is right in the middle. The area is, what's that, 75? Oh, yeah, thanks. 2. Oh, yeah, so this is, so the area is, oh, and you know what, also, what this really is a force. So I didn't multiply by G. So we have 30 times 9.81 is 294.3 divided by the length of 2 meters is 147.15 newtons per meter. So that's my real height. You've done that calculation a million times. 147.15. And so the area is, well, the original weight back, 294.3. And I'll redraw that free body diagram. We have a weight down of 294.3. RA here, RB here. And now we can do the table. So rho, force, moment. I'll use this as my about point. So for the force RA, rho vector is 0. Force is RAX, RAY. Cross product is 0. Then for the weight force, that's acting at 1 meter. So rho vector is 1, 0. The force is 0, negative 294.3. Cross product is negative 294.3. And then RB is acting at 2, 0. Force is 0, positive RB. Cross product is 2 RB. So we get RAX is equal to 0. RAY plus RB is equal to 294.3. RB is equal to 147.15. And so RA is equal to 0, 147.15. Okay, that doesn't shock anybody. So all we've done so far is figure out what those external loads are. This is all like old stuff. We did this a long time ago. Now we're going to go to the cut, okay? So now we have the external loads. Go to the cuts. And we have to think, how many of these cuts do we need? So between the endpoints, we have no point forces. No point couples. And no distributed load function changes. So that means that a single cut is going to work for all of this. We never have to switch cuts. Okay. So I just want to be clear on this. Like, if you look at this free body diagram, this is kind of what I was saying before. If you look at this one here, it looks like we do have a point force in between these two. Okay, and so it's an easy mistake to make to say, okay, we're gonna have one cut for the subfunction before this and one cut for after. But remember, this is already just a mathematical thing to let us do calculations. The real free body diagram is that. And so when you're looking for how many cuts to make, you always have to go back to the real free body diagram, including the distributed loads. Okay. Basically, like if you do it based on this, what you get is kind of like a pixelated version of what's going on. Like it's kind of like and since we only have two pieces, it's a very blocky looking approximation of what we have. It's not very accurate, you know. If you had 100 of these, it would be sort of like a numerical looking approximation of what's going on. But so we look at this free body diagram and we say, okay, one cut is all we need. We never have to switch subfunctions. Okay, so our cut one is valid for all x's between 0 and 2, not including the endpoints. And a representative free body diagram looks like this. We have 147.15 acting here. We have this downward distributed load acting here, and we know that the value of that is 147.15. We're skipping all this stuff, and we're skipping this. Yeah.
Wait, but I thought that the whole the beam was too.
Yes. So, right. So this is not saying that. What I've drawn goes from 0 to 2. What it's saying is what I've drawn goes from 0 to some x value, and that x value has to be somewhere in this interval. So this is going to represent everything from a tiny sliver of a piece to a slightly longer sliver to a longer piece to a longer piece to something that's 1.999 meters long.
Okay.
So this distance here is x. And what we isolate is always going to start all the way at the left end, and it's just going to go to this x. Okay. And then we need the internal loads too. I haven't put those in yet. So we have a tension, shear force, and bending moment. Now that we've chosen I mentioned that function q. So what's the function of x that gives us the height of this distributed load? This is like sort of the simplest possible case. Notice that our distributed load function q is just a constant function, 147.15. Okay, so that's the height of it, whatever x value you have. And I guess you would normally get that from this picture. And now that we've chosen the piece to isolate, now we can replace this distributed load with an equipolant point force. So let's think about this rectangle. Okay, the height of this rectangle is still 147.15. Last time, the length of the rectangle was 2, but what's the length of this rectangle? X, exactly. The centroid of this shape is right in the middle. The area is 147.15 times x. And so now I'll draw a new free body diagram. We have the joint force, 147.15. I'm replacing that distributed load now with this point force that has the magnitude 147.15x. And then the internal loads. And as far as distances, this whole piece has a length of x. So what's the distance from the left end to where that 147.15x is applied? It would be 1 if x was equal to 2. So it's half x, exactly. So x over 2. And so I'm going to always, on my cuts, do my about point at the left. So
when you do a cut, you always have to put your about point.
You don't have to. You never have to. It follows all the same rules we're used to. But if you ever have a couple spare minutes, just try doing a problem like this with the about point somewhere else, and you'll just see that it's much more of a pain, And so we will just always choose that as the about point. Okay, so I'm going to start with the 147.15. Row vector is 0. Force vector is 0. Positive 147.15. Cross product is 0. Then I'll do that one that represents the distributed load, 147.15x. The row vector is x over 2, and then 0 for y. The force is 0, negative 147.15x. And so the cross product is 147. I don't have it. Oh, yeah. So the cross product here is negative 73.575 x squared. Just notice I'm doing all the exact same steps that we did for rigid body statics. It's just instead of numbers, we have some x's mixed in there, And then the last, now we got to the internal loads. T, the location, the row vector for that is x, 0. The force vector is T, 0. Cross product is 0. Then V, that's also at row vector of x, 0. Force vector is 0, negative V. Cross product is negative Vx.
What V represent?
What?
What is V?
That is called the shear force, and it's one of the internal loads that we talked about last time. So, you know, if you go back to the notes from last time, you'll see a whole discussion of that. And then the bending moment, we don't care about these, and we just get counterclockwise bending moment. And now I'll start with Newton's second law. So it says 0, 147.15 plus 0, negative 147.15x plus t0 plus 0, negative v is equal to zeros. So t is equal to 0. V is equal to this function, negative 147.15x plus 147.15. And now the moment equation says negative 73.575x squared minus Vx plus m is equal to 0. Solve for m, and you get m is equal to v times x plus 73.575 x squared. Now substitute in the function v that we already calculated. So m is equal to the quantity 147.15x plus 147.15, all times x, plus 73.575 x squared. Multiply it out, simplify, and you get here that m is equal to negative 73.575 x squared plus 147.15 x. Okay, you get that because you have the 73x squared minus 147x squared. They partially cancel each other, and you end up with this.
Oh, do you require us to simplify like that, or is it fine the previous way? 'Cause,
Which way?
like, is it fine either way or no? Or do you
Like with the thing in parentheses?
Yeah. Do you
You're always going to get that partial cancellation, and actually, I'll tell you in a second why you would want to do this. So let's think about what these functions look like. Okay, we did that before. So for so if this is 2 meters, the internal tension as a function of x looks like this. It's just 0. I just haven't put any horizontal external loads in this stuff yet. The shear force as a function of x looks like this. So it starts at 147.15 and ends at negative 147.15. All I'm doing is reading, I'm just graphing this linear function here for v. Okay. And so it goes like this. And then the bending moment at the middle goes up to a maximum of 73.575. And it's a quadratic, so this is like a parabola. So it looks something like that.
Will the bending moment always be quadratic?
It will always be quadratic for uniform distributed loads. For other shapes, it'll be different.
Okay.
Professor,
Yes.
so when we do a internal loads problem, we need to draw these graphs?
Not always. Sometimes I'll ask you for them. On tests, I never ask you for them. You can just, when I ask you for them, you can just punch them into Desmos or something.
Could you please scroll up a little bit?
Yeah.
Thanks.
Wait, so for an internal loads problem, do you expect us to do it twice like we just did, or could we just do it the second one?
The first thing
Because we did the problem without experts.
Right. So those are calculating two different things. You're always going to have to do, first you're going to have to isolate the whole thing to calculate all the external loads.
Oh, I see.
Okay, so that's all we did was to figure out the joint
that was
forces.
That was just external.
Yeah, and that's like what we've done, all class. Then basically is when you start the internal loads. Okay, so from last time, we know that dm dx is, has to be equal to v. So let's check if that's true. D dx of the function, so the m function is negative 73.575x squared plus 147.15x. Take that derivative and you get negative 147.15x plus 147.15. And look up at the function for v, and that's what it is. So that equals v, and so check. That gives us a little more confidence, There's another relationship now that you need to know, and that is that also dv dx has to be equal to negative q. So q is that function that represents the distributed load. In our case, q was equal to just the constant 147.15. Okay? So we'll go negative d dx of the v function is equal to positive 147.15, and that's equal to Q. And so if both of those two derivative checks work out, then you're more confident in your answer. Okay, so what are the steps here? So first, isolate the whole body. To find all the external loads.
That's what we've already been doing.
Yeah, that's right. Then second, identify any spots where the subfunction will change. So those are any places between the endpoints where you have point forces, point couples, or changes to the distributed load function.
Would that just be like stuff acting down on it? Like,
Point forces?
Yeah.
Yeah, they could act in any direction. You know, I could have applied,
So
yeah.
so the only reason that gravity is not a point force is because it's like acting along.
It's really a distributed load, yeah. That's right. That we just haven't had to worry about it that way
You just put it
before.
in the middle to show.
Right. So we've always in the past just jumped from the distributed load right into making it as a point force, equipolant point force. But when you do the cuts, you have to be more careful with it. Okay, do your cuts. And calculate T, V, and M. And then last, do those derivative checks that say dm dx is equal to V and negative dv dx is equal to Q. Okay. If those checks work out, that doesn't mean that the problem that you definitely got the right answer. It just means that it eliminates certain stretches of the problem where you know you didn't make any mistakes, you know. But it helps. It can help you find stuff. Anybody have any other questions right now? Okay, that's it. So I'll assign a problem or two with uniform distributed loads, and then on Friday I'll go into some other functions, other Q functions.
Professor,